Hey guys, welcome to average value of a continuous function. In this lesson, we're going to be learning the mean value theorem for integrals. In semester 1, when we were learning derivatives, we learned the mean value theorem for derivatives, except that I didn't call it mean value theorem for derivatives because that's all you guys knew. So let's go ahead and do a quick review of what the mean value of derivatives was. So the mean value for derivatives said that you needed a function f, and this f had to be continuous from a to b on the closed interval from a to b. And f also had to be differentiable on the open interval a to b. So let me go ahead and draw a continuous and differentiable function. I'm going to start right here, and I'm going to maybe just draw whatever, it doesn't matter. Maybe not that. Maybe do another kind, like that. Okay, there's my function. It's continuous, it's differentiable. And if I met these two conditions, then there must be a c. There existed a c. That's an x value. There exists an x value c in a to b. In a to b, such that the derivative at c was equal to the average rate of change of the function from a to b. Now, what does this mean? You guys probably forgot what average rate of change meant. Average rate of change meant that if I got 2 points and I connected them, I have the average of these 2 points. And what the theorem's trying to say is that there must be at least one c. I'm going to do this in red. There must be at least one c such that the slope of this average rate of change was equal to the slope of the derivative, the slope of the tangent line. So that these two slopes were the same. And I know I did a kind of a poor job drawing it, but all the theorem was trying to say is that if your function is continuous from a to b and differentiable from a to b, then there must be a c such that the tangent line slope is equal to the secant, is equal to the slope of the secant. That's all that meant. And the theorem says there must be at least one c, so in this case there may be many c's. For example, maybe right here, another c. We can call this c1, c2. And somewhere right there we can draw another line that has the same slope as the other two. See, that was the mean value theorem for derivatives. But what is the mean value theorem for integrals? Let's go ahead and read. The mean value theorem for integrals says that if f is continuous on a to b, on a closed interval from a to b, then there exists a c in a to b such that the integral from a to b of f of x dx is equal to f of c times b minus a. Now, this probably did not make any sense to you guys, but I'm going to go ahead and explain it below. The geometric interpretation of the mean value theorem for integrals is that for a positive function f, there is a number c between a to b such that the rectangle with base a to b, and the height f of c has the same area as the region under the graph of f from a to b. So let me go ahead and draw a picture here. So let me draw a continuous function. And I'm going to redraw this function on the other set of x and y axis. Let me just move this over. So the mean value theorem says that there must be a rectangle which has the same area as the area below the graph of f. So when you guys learned integrals, you guys learned that when you're taking the integral from a to b, you're simply just taking the area under the curve from x equals a to x equals b. The mean value theorem for integral says that there must be a rectangle with base a to b, and some height f of c, we don't know what f of c is, some height f of c, such that the area of this rectangle is also equal to the area under the curve. That is what the mean value theorem for integrals is trying to say. So f of c represents some height of a rectangle, and b minus a, of course, represents the base of this rectangle. And if the base and this perfect height of the rectangle are to be used in an area formula, then we have the same area. So this is just a representation. This value f of c is called the average value of the function of f and is defined by this formula. Now, this formula and this formula are the same. Let me show you. The integral from a to b of f of x dx is equal to f of c times the b minus a. If I solve for f of c, then I have to divide both sides by b minus a, so that I get the integral from a to b of f of x dx all over b minus a, which is equal to this f of c. And we said that f of c was the average value, according to what this says here, is the average value. And that this equation here is equal to this equation, except that b minus a is factored out as a fraction. Let me go ahead and show you another representation using calculus in motion. Here we have a function that's continuous. This is the area of the function underneath the curve from a to b. Now, we don't know what this function, we don't know what the area is. Here's the area under the curve. But what do you think the area is if I took the average value of this function? In other words, pretend that this blue shaded region must equal this purple shaded region. How high would this height of the rectangle be in order for me to have the exact same area? So you guys are probably thinking, well, sir, you need to stop because I can't see. Well, I'm going to go ahead and stop. Maybe I think it's maybe like right here. I'm going to say that it's 0.5, 1, and 1.5. So now let me go ahead and show you guys the true average value, and let's see that if I'm correct. Here's the average value. It's going up and up and up, and I was just off by maybe, I don't know, 0.1 or 0.2 in my height. So this is my guess. My guess was 0.48, and the average value height should have been 1.64. So this, let me move this guess out of here. This area of the rectangle is supposed to equal the area under the curve. If I were to mold the area under the curve into a perfect rectangle from A to B as a base, then the height has to be 1.64. And that is what today's lesson's about, is finding the average value of the function. So let's go ahead and do one problem, and then on the next video I'll go ahead and show you an application of how we use average value to find certain solutions. Given the function 1 plus x squared and the interval from -1 to 2, find the average value of the function on the given interval. Okay, so let's just go ahead and write down, what does it mean to have an integral? An integral means to have f of b minus the f of a. So the definition of an integral means that you take its antiderivative and you plug in b, and then you plug in a, and you take the difference of those antiderivatives at those values. Okay, the average value simply has has one extra thing. All it has was a 1 over b minus a. b minus a. Now here's why they call it average value. This looks like the average rate of change, but it's the average rate of change of the antiderivative. So that's why it's called average value. So let's go ahead and use the formula that's given above. The formula above says that if I want to find the average value, I take the integral from a to b and I divide it by b minus a. So let's go ahead and change this f prime into what the actual problem is. So 1 plus x squared dx. We're going from a to b, so it's from negative 1 to 2. So this has to be 2 minus a negative 1. So let's go ahead and rewrite this as 1 over 3 integral from negative 1 to 2, 1 plus x squared dx. Order of operations says to do the integral first. So 1/3. The antiderivative of 1 is x. The antiderivative of x squared is x cubed over 3. And we're going from negative 1 to 2. And then we use the fundamental theorem of calculus to find the integral. Let's see, I might need a little more space. Okay, so if I plug in 2 for every x, it's going to be 2 squared minus, plus 2 cubed all over 3, and negative 1 plus a negative 1 cubed over 3. 1/3 is 4. Oh, not 4, not squared. I messed up here. It's not squared, it's just x. So it's 2 plus 8 over 3. And I'm going to distribute my sign already, so it's going to be plus 1 and then plus 1 over 3. And then all I have to do is combine my terms here. I have 2 plus 1 is 3. 8/3 plus 1/3 is 9/3, which is 3. And now I have 6 in the inside, and 1/3 of 6 is 2. 2 is my average value. 2 is my average value. Okay? This is my f of c. Okay? Now, part B says find c such that the average value is equal to 2, what I just found out in part A. How do we find c? C is supposed to be an x value. How do we find c given that f of c is 2? Well, let's go ahead and plug it in. F of c is equal to 2, which means 1 plus c squared is equal to 2. That is the original function here. I just replaced it with c, and I'm solving for c. So c is equal to 2 minus 1, c squared. You subtract 1 on both sides to get c squared is equal to 1, and c is plus or minus 1. Okay? And we're going to skip part C since I don't have a graphing calculator on me right now. But this will go ahead and conclude our first part of the video on the mean value theorem for integrals. See you guys in the next video.